So, good day, and this is Cadet Saavedra representing Group 10, which is a report of the manual radar plotting. So, first, we have to know we have to know our intended learning outcomes. So, first, the students should be able to understand the terms used in radar plotting. Second is the students should be able to know the basics of plotting using the radar plotting sheet. And third is the student should be able to plot. So for the definition of terms, R stands for relative vector for target vessel and T for true vector for target vessel also. CPA is closest point of approach and TCPA is time to closest point of approach. So what is relative vector? So the relative vector helps to find ships on a collision course. So the relative vectors and the associated CPA or TCPA data should be unaffected if the observer allows a fixed erroneous input of course and speed data to be applied. So what is true vector? So when using a true vector, the own ship and the other ship moves at their true speed and course. So the true vectors can distinguish between moving and stationary targets. So, closest point of approach. So, it is an estimated point in which the distance between two objects, of which at least one is in motion, will reach its minimum value of rated CPA. So, the estimate is used to evaluate the risk of collision of example a two ships. So, the shortest target vessel own vessel calculated distance that will occur in case of no change in course and speed data. So the CPA would involve a two ships. One is the target vessel and one is your own vessel. So the closest point of approach or the closest two ships will pass each other if both ships maintain course and speed. So if the CPA is 0, it means the two ships will collide. So a very small CPA may also mean a collision as a CPA is usually measured in using the radar input and therefore the reference point of the radar aerial of the bridge. So, in large ships, the bridge may be hundreds of feet from the bow of your stern. So, while the two bridges may pass clear, other parts of the ship will collide. So, time of closest point of approach. So, time to CPA in the time at which the CPA will happen if both ships maintain course and speed. So radar plotting. So this is an alternative to the ARPA, which is the automatic radar plotting aid. So with radar plotting, we aim to get all the information that ARPA can give. So the information are the following, which is the CPA or the closest point of approach and TCPA, which is the time of closest point of approach of targets. So the second is the course and speed of the target. So as you can see, the picture above is a radar plotting sheet. So this is the one that we use in order to fill up the CPA. We have to put our course, the targets, the TCPA, and others. So what we need is a radar plotting sheet, a pencil, a compass, and a ruler. When we see the target on the radar, we take the bearing and the range of the target and note down the time of observation. So we then plot this on the radar plotting sheet, and let us say that we noted following bearing or range of a target at 1800 hours LT. The picture depicts that we have noted the target, which is target A, the time, the range, and the bearing. So target A, the time that we noted for the target A is 1800 hours, and the range that we have noted is 8.0 nautical miles, and the bearing of the target is 060 degrees. Let's start plotting our observation. So we name our observation as O. So from the center, find the 60 degrees and then count the nautical miles and then put a circle on the 8 8 nautical miles at 60 degrees bearing. So the second observation of our target A is at the time is 1806 hours with a range of 7 nautical miles and the bearing is 059 degrees. And the third observation is 1812 181200 hours, 6.0 nautical miles and 057 degrees. So plot this on our radar plotting sheet and extend the line joining all. This is the line of relative approach of the target towards our vessel, which we have assumed at the center of the sheet. So now for our CPA, we need to find the closest point of the line of approach to the center. To do that, we just have to draw a line perpendicular to the line of approach and measure the distance of this line from the scale in the radar plotting sheet. So our vessel has a 330 degrees bearing. So the line that we have to from the CPA to the point of approach is at 330 degrees bearing. And the distance from the CPA to the point of approach is measured in the scale which is found in the radar plotting sheet. So our CPA here is at 0.8 nautical miles. So to calculate the TCPA, we just need to calculate the time required to reach at point C, considering it took 12 minutes to cover distance OA. So to do the measure, the distance, the C and the A, that would be 5.8 nautical miles in this case. Now with mathematics, we have to calculate the time the target would take to cover the 5.8 nautical miles with the relative approach speed. So this would be our TCPA. In this case, the TCPA would be 35 minutes. So it is at 1847 hours. So in getting our TCPA, we have to multiply 12 times 5.8, which is the 5.8 is the C to A, and divided by 2, which is the 2 nautical miles in O to A. So it is at 34 point, the TCPA would be 34.8 minutes or exactly 35 minutes. The course and speed of targets by radar plotting. So the next is we have to find the course and speed of the target. So to find that, from point O, we draw our course in the opposite direction and we have to cut the distance of the ship that traveled for the time period of OA, which is 12 minutes in this case. So let us say that our course is 45 degrees and our speed is 12 knots. So in 12 minutes, our ship would speed 12 knots and will travel through 2.4 nautical miles. So from point O, we have to draw our line in direction to 225 degrees and measure it 2.4 nautical miles. So we have to name this point as W, so such that the WO is our course. So our course is at 45 degrees bearing. So the perpendicular of our course is 225 degrees. So it is the bearing that we have to use in and put it and line it on the observation O and then plot it going 2.4 nautical miles down and then encircle it and name it as W. So now we have to join the W and the A. So WA is the course and speed of the target vessel. So we have to measure the distance of the WA and then the distance covered by the target in 12 minutes. So we have to calculate the distance it would travel in 60 minutes to get the speed. So from W to A, we have to connect it. So in this case, the course of the target is at 300 degrees and the speed is at 7 knots from WA, and it measures at 1.4 nautical miles. So in order to have more knowledge and information on the radar plotting or the manual radar plotting, please watch this video.
Welcome to today's video where I'm going to be showing you how to complete a radar plot. So for radar plotting, the first thing we need is the plotting sheet, which consists of the radar screen and a scale along the side. We're going to determine a couple of things in advance. We're going to be doing a 12-minute plot, and our own vessel is going to be doing 10 knots going 000, so due north. This means our own vector is going to be 2 miles long as measured on our scale, because in 12 minutes at 10 knots we would have travelled 2 miles. And then we're going to place it in the centre of the screen, pointing due north. This just represents our own true vector. The screen itself, we're going to take, it's roughly 6 miles. It's give or take a little bit just because of the dimensions of the screen though. But yeah, we're going to call this a 6-mile plot as well. So, as soon as we receive our first echo, we can't really determine much. All we know is the range and bearing of the target vessel. We need to continue to monitor to find more information. Then we find the next point. Again, we haven't quite got enough here. We're really working on scanty information at the moment. There's not enough to complete the plot. And then finally, 12 minutes after the initial plot, we get our third plot. So each of these plots is 6 minutes apart. The full range is 12 minutes, as we previously said. So all we're going to do to immediately find the CPA is we can join a line straight through the middle. And in this particular example, the closest point of approach is 0. If we do nothing, there will be a collision. Now, to find out how long until that collision, we need to measure a couple of distances. This first distance here, we need to find out how far the target vessel has travelled in the 12 minutes we've been plotting it. All we do, transpose that onto the scale, and we see in the last 12 minutes, the target vessel has moved 1.5 miles relative to us. Then, we need to find the distance that the target vessel has got to go from its final position until it reaches us. Again, we're going to transpose this onto the side scale and measure up to find it's about 3.3 miles. To work out how long it's going to take to travel that, we need to do a ratio between these. The ratio of 3.3 to 1.5 will be the same as the time to go to 12. And we simply lay it out like this. All we do is move the 12 to the other side, simple algebra here, to find the time to the closest point of approach, and running that through the calculator, rounding off to the nearest minute, we get 26 minutes. We can start writing these down the side. So our CPA, as we've said, is 0, and our time to the closest point of approach is 26 minutes. There's a couple more bits of information we need. The next ones are going to be the target vessel's course and speed. This is where vectors start to come into play. What we're going to do is we're going to start to label up parts of the diagram. We're going to call the first plot we received O. Reason for this is it's the original plot. It's the original position the vessel was in when we first saw it. The next point we're going to call A, because at the time of this plot, that is the actual position of the vessel. That's the last plot we received. They are actually there. Then we're looking for the other point, W. Now W to me doesn't really stand for anything apart from labelling the vectors themselves. And to find W, what we want to do is move our own vector pointing towards the O. And then the bottom of our vector becomes the W. The way to remember this is W to O is the way of your own vessel. W is going to be the point where we're doing all our vectors from, and O being the original position of the target vessel. To find this course and speed of the other vessel, we simply want the vector going from W to A. and we label that WA, which is way of another vessel. And simply the vector joins the two together. Now, as we know from maths, vectors are a component of distance and bearing, or speed and bearing. Otherwise it would just be a measurement, but no, a vector contains more information. So to find out the target's course, we'll transpose that vector to the middle, extend it out to the edge, and we can simply read off the edge of the diagram to determine their course. In this case it's 303 degrees. To find their speed, all we're going to do is measure the length of that vector, and we find it's about 1.1 miles. They've done that 1.1 miles in 12 minutes. Now, of course, to get 12 minutes to an hour, you multiply by 5, so we times both by 5 to get 5.5 knots. Now we've found their course and speed. The next things we want to find are the bearing at the closest point of approach and the aspect. Now, in this particular example, where the closest point of approach is 0, there is no bearing, so that one is actually irrelevant. If the closest point of approach was, say, a mile, then we'd want the bearing to where the vessel would be when they were 1 mile off us. We will cover that when we look at a more advanced plot. And the final thing we want is the aspect. Now, the aspect's a little bit tricky because of all the workings out we've done on the screen so far. We actually want to change things up a little bit. And all we're going to do is move the target vessel's vector onto their actual position. Now, if you look at this, this looks actually exactly like a normal radar screen, where we've got a relative motion plot, where relative to us all the dots are moving, but the vectors are true vectors. We've got our own true vector and the target vessel's true vector. Now, the aspect is going to be the bearing we are from the target vessel. So to find that, all we're looking for is the angle between their heading, or their course, and the bearing to us. And we can either measure that directly from this position, or we can transpose their heading to the centre and extend the lines out where we've got a nice gauge of degrees around the edge, and all we want is the difference between these. Now, you'll note that the bottom line doesn't quite go through 225 where it should. This is just because of the dimensions of my diagram, but we know it's the reciprocal of the bearing we've been detecting the target, so it should actually be 225. So to find this out, all we do is 303 minus 225, and we get 78 degrees. Now, we know we're on their port side, so we're just going to label that as red 78 degrees. Now, after all that, we've completed the plot. Completing the plot simply means finding the closest point of approach, time to the closest point of approach, target vessel's course and speed, their bearing when they're at the closest point of approach, and their aspect. In other diagrams it would be more difficult to find these, and we might have a CPA that's not quite 0. Now, to confirm all this, let's just swap it out from a radar plot and look at the overview of the vessel situation. We can see there's two vessels, both moving ahead, but they're on a steady bearing, so risk of collision exists. So of course we know from the collision regulations the action to take is the red vessel is going to come round to starboard, and then both vessels will be clear to continue until they're finally passed and clear.